Maybe you've seen a diagram that looks like this one. This is a representation of perspective shown in an orthographic side view. That means we've taken parallel lines. These are supposed to be parallel lines above the horizon, and then converted them into what they would look like when you account for perspective. So we see that these lines that we know are parallel are converging down to a vanishing point. So then we see right there the sun, which is moving along one of these parallel lines. It's moving along at a fixed distance above the horizon, aims downward because of perspective, and heads towards that vanishing point. And then after the vanishing point, we see that the sun goes below the horizon. And this is all due to perspective. Now let's check this. Here's another one. Very similar diagram. These are parallel lines having been tipped down towards a vanishing point because we know that perspective does that. So here we see the sun and those converging parallel lines as it crosses the vanishing point. So my question then is, if this is correct, if this diagram is an accurate representation of perspective and how perspective bends straight lines together into a vanishing point, then where is this vanishing point? This point, where all lines converge, is shown to be a fixed distance from the viewer. And if that's the case, we should be able to measure that distance and tell exactly where this point is. So I decided to try to empirically determine the distance to the vanishing point and see if I could do an experiment to validate those diagrams. This is the experiment that I've come up with. Just take a photo that shows a perspective. All we need is a repeated element of the same size, repeated as it moves into the distance. Choose anything of a repeated size that's at a fixed distance apart. These Legos, I just placed them along the floor at 2-foot intervals. So they're all the same height and they're all the same distance apart. Just take a picture and then load it into any software that you can use to measure the height. Or, you can even just print this out on paper and measure it with a ruler. It doesn't have to be all that precise. Just measure the height of each one of these elements and write down your numbers, like this. Here's another example where I laid out some Legos on a table. These are 5 inches apart. In this case, I used the outside of a building to get much larger sizes. And here, I don't actually know the spacing in between them, but that's not really important. What's important is that I know that they have a regular spacing in between them. Now that we've got our measurements, let's make a graph of it. We should be able to extrapolate from that graph to see where the intersection with the horizontal line should be. This is the results for the first sample of the Legos along the floor at 2-foot intervals. And we can see that this line isn't straight. That's going to make it a little bit more difficult to find the intersection. So let's take a look at some more results. Here's that first one of the Legos along the table with that curve shape. Here's the second one with the Legos along the floor with 2-foot separation in between them, and again it has the exact same curve shape. So how about the buildings with much larger separation? Again, we see this curving shape. So how do we extrapolate this out to where it intersects the horizon? Where is that vanishing point? So we've seen that this relationship between the apparent height of an object and its distance from the viewer is not a straight line at all. It's some kind of curve. but what kind of curve is it? To me, this looks like an inverse relationship. An inverse relationship just means that whatever's on the y-axis has whatever's on the x-axis in the denominator, like this. Some kind of division. And I'm wondering, could this be as simple as the apparent height of the object is inversely proportional to the distance from the viewer? Meaning, if the object in the far distance is twice as far as the object in the near distance, height, the apparent of the far object, is 1/2 that size. Or, for example, let's say the far object was 10 times farther away than the near object. The apparent height of the far object is 1/10 the size of the near object. Let's put that theory to a test. Here I've taken the data, the raw data from this image, and I've taken this first sample, that's the height of this beam, and I put that in right here. And then for the rest of the curve, I'll use this equation. That's this red line right here. So how did we do? Blue dots are the actual measurements, and the red line is the theoretical equation. That looks like a pretty good fit. Here's our Legos on the floor. These are the actual samples measured from this photograph. And here's the curve. Here's the Legos on a table. These are now the smallest distance apart. These are 5 inches apart. Actual samples and the curve. So this seems pretty solid. The relationship between the apparent height of an object and its distance from the viewer is an inverse relationship. And an inverse relationship is not a straight line, it's a curve. Okay, now that we have this formula, we should be able to calculate where that vanishing point is. This is our formula. So I want the vanishing point. The vanishing point is when the height of the far object approaches 0. The object vanishes. So if the height of the far object is 0, that gives us a 0 on this side. So I want to calculate what is the distance to the far object at the time that this reaches 0. And the only way to get this equation to go to 0 is to let the distance to the far object approach infinity. So the vanishing point is at infinity. Here's another test that was sent in by Bobby Shafto from San Diego. He took this wire mesh and measured its distances and made this chart. And here's his curve. He took another one from something he saw online of 2 mirrors reflecting back and forth to create this infinity image. And this is the graph he made from that one. So now we know that perspective does not make distances shrink in a straight line towards the horizon, but instead on a curve that approaches the horizon. We also know that that curve only reaches the horizon as you go out to infinity. It never crosses the horizon. So what does that mean for this image? This image assumed that we would get the straight line curve, a straight line curve that would cross the horizon and then go beyond. But we just saw that it doesn't. These lines, these parallel lines, should have been projected like this. The lines curve down towards the horizon, getting ever so closer, but never actually reaching. And how about the ground? The ground should come up towards the horizon, gradually approaching, but never quite reaching. And the sun? Here's the sun. I've placed it along the top line, and as the sun moves into the distance, it should, if it was at a fixed parallel line above the Earth, we should see the sun gradually lowering, easing towards the horizon, but never quite getting there. We should also see the size of the sun getting smaller and smaller and smaller as it approaches that horizon, but again, never crossing it. So what does that mean for this image? Well, simply put, this image is wrong. We did the measurements and we showed that the vanishing point is at infinity. And that little sun there, if it really was moving at a parallel line above the Earth, it would have to be curving down towards the horizon, but no matter how far away that sun got, it could simply not cross the horizon. It cannot. There is no way for that sun to go past infinity and end up down below the horizon. So what does that mean for the flat Earth idea that the sun stays at a certain level above the Earth and it just seems to go below the horizon because of perspective? Well, we just showed that perspective cannot do that. Perspective by itself could make an object above the horizon seem to ease down towards the horizon and only reach the horizon as that object got out to infinity. But it can't make the object go below the horizon. And that just doesn't work for this model. And the explanation for this is as obvious as you'd think. The Earth is round, and as it orbits the sun, it rotates, causing that sun to rise in the east and set in the west, just like you've seen every morning and every night.